In this video, we're going to talk about rate laws. So a rate law is an equation that shows how the reaction rate is dependent on the concentration of each of the reactants in our reaction. So say, for example, we have our generic reaction here, where we have our two reactants A and B, and they react to form some products. And we don't really care at this point what the products are. Well, the rate of that reaction is proportional to the concentration of those reactants. We can write a rate law for this reaction, and a rate law takes the form: the rate is equal to K, which is a constant, and that constant would be specific to that reaction and to the temperature at which that reaction takes place. Now, A and B are raised to some power, the concentrations of A and B. But notice the letters here. We have M and N. Notice those are not the same as the coefficients up here. That is because you cannot take the exponents from the coefficients of the equation. So do not base your exponents in a rate law. On the coefficients. Those exponents can only be determined experimentally, and we're going to show on the next few slides how we determine those exponents. But this is the form that a rate law will always take. The rate is always going to be equal to some constant times the concentration of the reactants raised to a power. And K is a rate constant, lowercase k. And be very careful, make sure that when you're writing your rate laws that you write this as a lowercase k. Capital K refers to something completely different that we'll get to in another chapter. So as I said, the values of the exponents can only be determined by experiment. They cannot be determined from the stoichiometry of the reaction. And if you look at some of the examples down here, some of them end up being what happens to be the coefficient, but a lot of them aren't. For example, if we look at the rate law for this first reaction, we see the concentration of CH3,3Br. But if we look at the reactants here, H2O is also a reactant, but it's not even shown. The same thing happens in the second reaction. If we look at the third reaction, Br negative has a coefficient of 5. There is no 5 superscript here. H plus has a coefficient of 6, but the superscript is 2. Okay, so these do not come from the stoichiometric coefficients. They must be determined by experiment. So let's look at an experiment and see how we would determine what those exponents should be. So we've got 4 experiments here, and we're given the initial concentrations of nitrogen monoxide and O2, and we're given our initial reaction rate. So let's take a look at the first 2 experiments. If we look at the first 2 experiments, we keep the concentration of O2 the same. And we double the concentration of NO. So what does that tell us about what this exponent should be? Well, we also have to take into account how the reaction rate changes. So if we look at the reaction rate, it goes from 0.024 to 0.096. So we have to keep one of the reactants the same. You can't change both reactants at the same time. What you want to see is if you keep one of the reactants the same and double or triple or quadruple, we can do any of those. But if we keep one reactant the same and we change the other reactant, what is the effect on the reaction rate? So for keeping O2 the same, which we are in the first two reactions, the concentration of NO doubles in the first two experiments. So we go from 0.015 to 0.30. So that concentration has increased. Now let's look at what happens to our reaction rate when we keep the concentration of O2 the same and double our concentration of NO. We go from a rate of 0.024 molar per second to 0.096 molar per second. So this is, and if you can't do this in your head, put this in your calculator, 0.096 divided by 0.024. That comes out to be a change of increasing the reaction rate by 4. So we're increasing the concentration of NO by 2, and we're increasing the reaction rate by 4. So we can write an equation, 2 to the m equals 4, and we want to solve for m. So this is how you will always write this out. Now in this case, if you think about what exponent here would give you 4, and if you think about if you square something, 2 squared would be 4 because 2 times 2 is 4. So in this case, you could work out without having to do any math what m is. You can kind of just look at that and tell. But what if it was a situation where you couldn't just look at this and tell? Well, what you would do is you can determine this by logs. So we have 2 to the m equals 4. So we can take the log of 2 to the m is equal to the log of 4. So we take the log of both sides. Now when we do logs, there's a rule with logs that exponents can come out front and be multiplied. So we would get m log of 2 equals log of 4. And then we divide both sides by log of 2 to get m by itself. So m is equal to the log of 4 divided by the log of 2. So log 4 divided by log 2, if you put that into your calculator, gives you 2. So if we double the concentration of one of the reactants while keeping the other reactant the same, and the reaction rate quadruples, then that reactant has an order of 2. Let's take a look at O2. So if we look at the first and the third experiments, we have our concentration of nitrogen monoxide being held constant. So we have to hold one of them constant. And in this case, it's going to be the NO. When we do that, we take the concentration of O2 from 0.15 to 0.03, from 0.015 to 0.030. So we double the concentration of O2. Look at what happens to our reaction rate. We go from 0.024 to 0.048. So we doubled our reaction rate. So in this case, when we double the concentration of O2, we double the reaction rate. Well, the only thing the exponent can be here is 1, because if it were any higher than 1, this would not equal 2. So, if you double the concentration of one of your reactants while keeping the concentration of the other reactant the same, and the rate doubles, then we have a reaction order of 1. So we don't write the 1 in. We typically leave out 1s and they're just understood to be there. So for this reaction, we would have a rate is equal to the rate constant times NO squared times O2. So we have now our rate law for this reaction. So the reaction would be said to be second order with respect to NO and first order with respect to O2. So the overall reaction order, if we add the 2 for NO plus the 1 for O2, the overall reaction order is third. So then the other question that we need to answer is, what are the units for K? So if we're looking at K, if we rearrange this equation to get K by itself, we have the rate over NO squared times O2. So the units for rate is molar per second, and the units for NO would be molar, but we have to square that since NO is squared, and the units for O would also be molar. So one of these molars cancels with the other molar. Second, since this is on the bottom of this fraction, comes down to the bottom, so we're left with 1 over molar squared times second. And this is for a third order reaction. So this table here shows you the units for K for each of the rate laws. You don't have to memorize these because you can work them out if you just write out your rate law, but you do need to be familiar with the units for K, so you can either work them out or you can memorize from this table. Now, what if we have a 0th order reaction, which means that the rate is not dependent on the concentration of that particular reaction, of that particular reactant? So if we apply the concentration of our reactant versus time, so we plot the concentration of our reactant on the y-axis and time on the x-axis. If we do this for a 0th order reaction, the slope is equal to the negative of the constant. So this is one way we can determine the constant for a particular reaction, is we can make a plot of the concentration of one of our reactants versus time. We have to determine what the order of the reaction is first. If it happens to be a 0th order reaction, the slope is equal to the negative of the constant. So what we're saying with a 0th order reaction, as I mentioned, is that the rate is independent of the concentration. In other words, it doesn't matter how much we change the concentration of our reactant. It's still not going to make the reaction go any faster. So in other words, for a 0th order reaction, the rate is simply equal to the rate constant. Or we can put this as the decrease in the change in the concentration of our reactant over the change in time is also equal to the constant. So for all of these reactions, whether 0th order, 1st order, 2nd order, we can write an integrated rate law. I'm not going to go through the derivation of that because it's really more than what we need to deal with at this point. all that you really need to know is the integrated rate law. So if we do this for a 0th order reaction, our integrated rate law is the concentration of our reactant with respect to time is equal to the negative of the rate constant times the time plus the concentration of our reactant at time 0. And time 0 is our initial concentration. So the nice thing about these rate laws when they're written in this form is that they form a straight line. So if you think about your equation for a line, the equation for a line in algebra is y equals mx plus b. So if we write our reaction, our integrated rate law for our reaction, and we plot this, if we plot the concentration of A at a particular time, and we plot the concentration of the time T as our X, so we plot T as X and the concentration of A is Y. The slope of our plot is equal to the negative of the rate constant, as we mentioned. And the y-intercept, which is represented as B, is our initial concentration of A. So if you were to look at a plot of a 0th order reaction, where you have time on the x-axis and the concentration of your reactant on the y-axis, the slope of that graph is going to be equal to the negative of your constant, and the y-intercept will be your initial value of your reactant. So to give you an example of a 0th order reaction, because that might seem a little odd that the order of your reaction doesn't depend at all on your concentration. Let's look at an example here. We have ammonia molecules that are in the gas phase, and that breaks down into nitrogen gas and hydrogen gas. Well, the only way that this works is we need a catalyst. So we have our solid surface here, and the ammonia molecules will react with that solid surface. Well, it doesn't really matter how many ammonia molecules you have, because you can increase this all you want, but if there's no space on the surface to react, the reaction's not going to go any faster, because the only molecules that are going to react are those that are on the surface of this metal here. So the reaction is actually going to depend on just on the ammonia molecules landing on the surface and breaking down into an H2, not on how many ammonia molecules we have in the gas phase. So now let's talk about our first order reaction. So we have our reactant A that forms some product, and we're not going to worry about the products because rate laws are always based on the reactants. So the rate is equal to the rate constant times the concentration of A, or we can express this as the negative of the change in the concentration of A over change in time, is equal to the rate constant times A. So again, we can derive an integrated rate law, and I'm not going to go through the derivation. We'll just look at the actual integrated rate law. So the integrated rate law is the natural log of the concentration of A at time t over the concentration of A at time 0 is equal to negative kT, where the concentration of A at time t is represented with a T subscript, and our initial concentration is at time 0. Now, this form is not particularly useful to us. We like things in a form where we can graph them, because that makes our lives much easier when we need to determine things like the slope and the initial concentration. So I won't go through all the steps to rearrange this. But the form that we actually use, and that's most important, is the natural log of a at time t is equal to the negative of kt plus the natural log of a at time 0. So this form is much more useful to us because if we plot the natural log of a as our y and t as our x, so t is time, so we're going to put time on the x-axis and the natural log of a on the y-axis, then what happens is our slope is again equal to the negative of the constant, and our y-intercept, which is b, is equal to the natural log of the concentration of our reactant at time 0. So this form is much more useful to us than this form that puts things in a format where we can't really graph them. So this form down here is the form that we will primarily be using. So again, as I mentioned, this allows us to give us a graph that's a straight line fit, and the slope ends up being the negative of the rate constant. So if we were to plot just the concentration of A versus time, we would get a curve, not a line. So this is why we use the natural log for first order reactions. We really don't like graphs where it's not a straight line, because they're just not very useful. Straight line graphs make our lives very simple because the slope usually tells us something important. In this case, the rate constant, the y-intercept usually tells us some value. But if it's not a straight line, you can only take the slope at some point, which doesn't really help us. So we like things that make our lives simpler and that are useful to us. So even though it means we have to take the natural logarithm here, we do that because now our slope is equal to the negative of our rate constant, and this y-intercept here is the natural log of our original concentration. So to show you a graph of some data here, if we have our reaction that we talked about earlier, N2O5 gives us NO2 and O2. If we look at the concentration of N2O5 over time and we take the natural log of that, since that's what we need to plot, we plot the natural log of N2O5 versus time. The slope of this would be the negative of our rate constant. And the y-intercept here is the natural log of our original concentration at time 0. So we can calculate the slope, and there's a couple ways we can do this. We can do it manually if we take the values at 2 points. So this is at time a little over 600, so maybe about 650, and time about 175 maybe. And then we can take the natural log of N2O5 at those points. Okay, so 650 and 150. And our natural logs are 5.02 at 650 and negative 4.17 at 150. So the other way you could do this is if you're doing this in Excel, then you can actually tell Excel to put a trend line on here, and it will give you the trend line with the slope, which is kind of nice. And we may play around a little bit with that in class, so that you can see how Excel would do it. So if you do the calculation, it comes out to 0.0017, which is our rate constant, but this is the negative of our rate constant, so we have to make it positive in order to give us our actual value. And if you took any 2 points on this line, you would get the same value. Now, first order reactions are also particularly special in that their half-life is something that is easily calculated. So half-life is the time that's required for the reactant concentration to drop to 1/2 of its initial value. So if we start with a certain concentration, the time it takes for the reactant to get to half of that concentration is our half-life. So if we take our initial concentration and we're going to represent T as T1/2 since we're talking about the half-life. Well, A at T1/2, by the definition of half-life, is the initial concentration of our reactant divided by 2. So we can rewrite this equation, and I'll write it up here. We would have the ln of A sub 0 over 2 over A sub 0 is equal to negative KT. But A sub 0 is the same on the top and the bottom. So this cancels out, and we're left with the natural log of 1/2 is equal to negative KT over 1/2. Sorry, negative KT 1/2. Now, if you put the natural log of 1/2 into your calculator, what you will find is that comes out to 0.693. Now, there's a few more decimal places to that, but 0.693 is enough for our purposes. So this comes out to 0.693 equals negative KT 1/2. And if we want to get T1/2 by itself, and this actually comes out to negative 0.693. So if we divide both sides by negative K, negatives cancel out, and we're left with T1/2 is equal to 0.693 over K. So we can calculate the half-life of something that is a first-order reaction if we know the rate constant. Or if we know the half-life, we can calculate the rate constant. So for a first-order reaction, it's nice because half-life is independent of the initial concentration. So each of the successive half-lives is an equal period of time. That is not true for other orders of a reaction. So this is why we mainly focus on the half-life of a first-order reaction, because this is the only one where the half-life is the same period of time for each of the half-lives. So for example, if we look at something like carbon-14, so carbon has an atomic number of 6, which means that carbon-14 has 8 neutrons. That decays into nitrogen-14 plus an electron, and has a half-life of 5,715 years. So we can take the decay rate as the change in nitrogen over time, and we could use this to calculate the rate constant since we know what T1/2 is. So now to talk about second order reactions, which is the last piece we're going to talk about in this video. If we have the concentration of A going to some product, in this case it's a second order reaction, so the exponent is 2. So again, just like with our 0th order and our first order, we can represent this as the negative of the change in concentration of A over the change in time is equal to the rate constant times the concentration of A squared. So we can use this to derive an integrated rate law, and we're just going to get to the integrated rate law and not worry about the calculus of getting there. So if we plot 1 over our concentration of A as Y, and again we calculate concentration of, we plot T as X. So we plot T as X, we plot the concentration of 1 over A as Y. K is equal to the slope, and 1 over the initial concentration is our y-intercept. So in this case, we have to plot 1 over the concentration, which is time. But our slope works out to be k. Not negative k, but just k. So that gives us our rate constant. So let's look at a reaction here where we don't know whether it's second order or first order. So if we take our concentration of NO and we plot the natural log of NO, the natural log of NO2 and 1 over NO2. Well, if we plot the natural log of NO2, that gives us a curve. So that tells us this is not a first order reaction. So when you're trying to determine if something is second order or first order, what you can do is make a plot of the natural log of the concentration of the reactant and 1 over the concentration of the reactant. The one that is the straight line gives you the order of the reaction, because if that's the correct order, then plotting 1 over NO2 or natural log of NO2 would give you a straight line. So if we go back to the natural log of NO2, this is not a straight line. So we can immediately say that this is not a first order reaction. This, if we plot 1 over NO2, does give us a straight line fit. So this is a second order reaction. And the slope of this is the rate constant. So we could calculate the slope, or we could just plot a trend line for this and get the slope. So if we calculate it, we take a value at 150 and 340, which is just we've picked in this instance. So you could pick any two values, and we do 400 seconds minus 50 seconds. We get a slope of 0.541 over molar times second. So the half-life for a second order reaction, we can write an equation for that. But you'll notice that the concentration of our reactant appears in that equation. So this is the equation for the half-life of a second order reaction in this box here. We don't deal with it too often, although occasionally you might see that. The difficulty with a second order reaction is that each of the half-lives is a different length of time. Each succeeding half-life is twice as long as the one before it. So it makes it a little less straightforward than dealing with a first order reaction because they're not the same amount of time. So we will deal with the half-life of a second order reaction sometimes, but not very often. We will mostly, for half-lives, only have to worry about first order reactions. Now you will need to do the integrated rate laws for zeroth, first, and second order reactions. So this table here summarizes all of what we've talked about. So you have your rate laws, your integrated rate laws, which is the useful part that we will need to do. It shows you which graph is linear. So if you're asked whether something is zeroth order, first order, second order, and you've got a lot of data, one way you can deal with that is to make a graph. If the concentration of A versus T is linear, zeroth order. If natural log of A versus T is linear, that's a first order. And if 1 over A versus T is linear, that's a second order. So this part is something that we will use quite frequently as well. For half-life, as I pointed out, only first order has a half-life that is constant. So we will not deal with half-lives as much for zeroth order and second order. We'll see them occasionally, but most of the time, if you're asked about half-life, it will be a first order reaction. So we're actually going to stop here, and we will put these rate laws to use and get some practice dealing with some of these integrated rate laws and doing some calculations and determining rate orders in class. So I will see you in class.